So a second thing we're going to care about is the momentum thickness. So once again, we're going to get the equation and then we're going to give an understanding of kind of what it is and what it's doing. So momentum thickness. Yes, I just forgot how to spell momentum for a second there, and I remembered. There we go. And it's theta. Why theta? Because they hate you and they just wanted to try to use. We ran out of symbols, okay? We ran out of symbols in the Greek alphabet. We had to keep on reusing them. I voted for us to keep on using new alphabets, but they said that would be a bad idea. Because yes, I was around when we chose all the symbols for all equations. So it's equal from the integral from 0 to y, once again, some distance. And I'm going to go, it's rho u over rho e u e times 1 minus u over u e dy, where delta is less than this distance we're going to, as this number approaches infinity. So y is going more or less to infinity. It has to be more than delta, as in more than our boundary layer, for us to figure this out, and it's supposed to be big. It doesn't have to be actually infinity, but it's just going to the point where I've gotten past all these changes. Okay, so let's go ahead and draw this out and see if we can figure out what's going on here. So I'm going to bring in my infinitely thin flat plate, and I'm going to have, let's see. Yeah. Yes, we'll do it this way. And I have my boundary there. And then I'm going to have some mass flow here. So I'm going to pick a tube like this. This is dy, kind of. I'll just say that's y. Makes it simpler. And I have a mass flow rate that is flowing in here, which will just be rho e ue right here. Ooh. Not quite nice right there. Rho e ue. Beautiful. Okay. That looks pretty good. Okay, so that is kind of like my mass flow rate, but what about momentum? Well, momentum is a little bit easier. Momentum is mass times velocity, and so you can kind of get the idea our analog here is going to be mass flow rate times velocity. So that's going to be equal to rho e ue times qe. Okay. Make sure I don't completely butcher this guy here. Yes, that looks good. Now, on the other side, exiting this one is going to be rho u times u. That looks fine. That should be okay. Yep. Though I did make one little error here. No, that's good. Ah, yes. One of these should have been u. There we go. Okay, sorry about that. Yep. Bin's gone. Okay, so I have my momentum going in. I have my momentum going out. What you might think is that there's probably going to be less momentum going out than there is going in. Why is that? Well, momentum only changes if there's a force, so that kind of gives you an idea of where we're going here. And so I can, if I want to, go ahead and take the difference between these two. So if I do that, and I write down my equations correctly, and I don't mess something horribly up, let's see here, I would get a difference here. So I'll call it momentum difference. That's going to be equal to rho u ue minus rho u. Okay, both of these have these guys in common. I wasn't supposed to have an e there, my bad. And so I'm going to pull them out. And so that becomes rho u times ue minus u. Okay, So this is the momentum difference from one side to the other. Oh, as long as I integrate it, because we're supposed to integrate it. And just like last time, we are now going to define a term that helps us just deal with this. And so we're going to say, okay, so this momentum difference, it's the same as if I had the following. So I have a block here, and it's coming in at rho e, velocity ue. And what's happening is it's kind of like I have missing momentum when I come at the end. So I have some thickness right here, which I'm going to call theta, which is simply saying I don't have like any momentum here anymore. And so what's coming out is going to be equal to rho e, let's see here. So what's missing, my bad, ue squared times y minus theta. So the missing portion is all due to that theta term, because I've gotten rid of it now. So I'll write that out. So I say integral from 0 to y, rho u, ue minus u, dy is equal to rho e ue squared times the momentum thickness. So when we solve, we get that theta is equal to 0 to y1, rho u, rho e ue times 1 minus u over ue. Okay, dy. There's our momentum thickness. We come back to it again. So it's kind of like this missing momentum. It's you also say it's like the height of a stream tube that's carrying our missing momentum. Like there's a stream tube here that's gone somewhere else that's carrying it. And so all that's great, but the key thing here is that it's all about a change in momentum. And hopefully you remember that force is simply equal to the time rate of change of momentum, which is more or less what we have here. So while it's not perfectly connected, my momentum thickness is proportional. And let's see, make sure I do this right, right. Momentum thickness right here is proportional to my skin friction coefficient. So my momentum thickness is going to be proportional to my overall skin friction coefficient. That is lowercase. And this one right here is the uppercase because it's all been integrated. So the higher the momentum thickness I have, the more missing momentum I have, and therefore the greater force that my surface has to exert on the flow to do that. Because when I'm looking at my flow here, the only thing that is causing a force from one side to the other, the only thing that can cause a change there is this surface. And it is pushing on the flow, and of course the flow is then pushing on it and causing drag. And so my surface is what is grabbing the flow, slowing it down as it passes, and causing this momentum thickness. And so the thicker it is, the more energy my surface has to impart to slow it down. So also the thinner is, the less we're slowing down the flow, and therefore the better we're cutting through it. So we want to have a thin momentum thickness if we want to have low skin friction drag.